Alright, unlike last time, we're not doing rules of implication. No, instead today what we're going to do are the 10 rules of replacement, and then we're going to see how we can incorporate them into our proofs. So let's just get straight into it. So what are the first 5 that we're going to do? So the first one we'll do is De Morgan's. So we have De Morgan's rule. De Morgan's, and we're going to denote that our shorthand will be DM. Now, what actually is De Morgan's? Well, here's what De Morgan's tells us. It tells us a couple things. If we negate a conjunction such as P and Q, this is logically equivalent, and we're going to denote the logically equivalent with that like 2x2 grid of dots. This is logically equivalent to not P or not Q. Likewise, not P or Q is logically equivalent to not P and not Q. And this is something that you could check with like a truth table. You can see that not P and Q is logically equivalent to not P or not Q, as we have done in the past to check for logical equivalencies. So that's going to hold true with all of our rules for replacement. We're going to show how statements are logically equivalent to other statements. So the next one we want to look at is commutativity. Commutativity. This one you may remember from math. You remember the commutative law? Commutativity. Well, that's what we're going to incorporate into logic. Now, commutativity tells us that if we have something like P and Q, that is logically equivalent to Q and P. You could switch the order. If you have something like P or Q, well, that's logically equivalent to Q or P. So you can switch them around. Now, with commutativity comes associativity. Associativity. Oh, and I did not give the shorthand for commutativity. That's just going to be comm with 2 M's. And associativity, we'll do assoc, so it'll be A-S-S-O-C. Now, the associative laws from math, right? If we have P or Q, let's change our color. If we have P or Q or R, this is logically equivalent to P or Q or R. Likewise, if we have P and Q and R, this is logically equivalent to P and Q and R. So basically we can shift the parentheses around. The order doesn't matter. In this case, we can choose what we want to do first. Now we've done commutativity and associativity. So next, of course, will come distribution. Distribution. And we'll use dist for that. Now, what does distribution tell us? If we have something like P and Q or R, that's going to be logically equivalent to P and Q, or, or P and R. And likewise, if we have P or Q and R, that is equivalent to P or Q and P or R. Now, finally, we've got one more rule of replacement that we're looking at right now. What is that going to be? That is going to be double negation. Double negation it's intuitive. It makes sense. It tells us that if we have something like this, if we have not P, that's equivalent to P. And by the way, these equivalencies, these relations, they go back and forth, right? So it tells us if we have P, we can replace that with not P if that's going to help us, and it just might. And we denote double negation with DN. Now, before we actually get into a proof using these rules of replacement, we should talk about the difference between rules of replacement and rules of implication. So, basically, let's say I have something like this, right? If I have A, then B, then C, right? And then I have B. You might be tempted to deduce C, right? You might be like, oh, using 1, 2, and modus ponens. You know, put that in parentheses. Modus ponens. But you can't do that. You cannot just use rules of implication within a line, right? And we still have that whole other part of the line there. We have A then, and we just completely disregarded that. We're going to be able to conclude C without without A there first. No, we can't do that. This would be invalid. But the thing is with the rules of replacement, you can change things within a line, right? So if I had something like, oh, I don't know, I had A and what do I want? I want A, then P or Q, right? Say that's my statement. What I can do is on line 2, I could say A, then Q or P. And what does this come from? This came from 1, and this came from commutativity. So with rules of replacement, you can change stuff within a line, and that might help you in a proof. But with rules of implication, you cannot just change things within a line. You must operate on the entire line. I hope that makes sense. Now what we're going to do is we are going to do a proof. So let's get all of this out of the way for a second. We're going to do 3 proofs because they are like really fast. So the first proof we're going to look at, what do we want our premises to be? Well, our premises are going to be not M. So we have not M, then P. And not N, then Q. Our second premise will be not M and N. And then the conclusion we want to get to is P or Q. So let's do this in blue. Let's show our steps. Okay, what's the first thing we can do? Well, I see that we can do De Morgan's law on line 2, and that's going to help us because we will have not M or not N. So this came from line 2 and De Morgan's. And then what we have here, we have a constructive dilemma using lines 1 and 3. So from lines 1 and 3, what we can deduce is P or Q. They came from 1, 3, constructive dilemma. And see, that was a super short proof. That's why we're doing 2 more, because they're also like 4 lines, I think. We have, let's do not, N, and T. And then for our second premise, we'll have T, and what we want to conclude is not N. So how are we going to go about doing this? Well, again, the only thing I see we could do first is De Morgan's. So on line 1, we get not N or not T, and this comes from line 1 and De Morgan's. Now, another thing we can do, right, on line 2 is double negation. We can make this not T. That comes from 2 and double negation. The reason we're doing this is so we can incorporate a disjunctive syllogism. Now, remember in the past I said we need to stick to a specific form, right? If we wanted to do disjunctive syllogism for not N or not T, what we would need, right, so if we had like P or Q, what we want, right, is not P, and then we can conclude Q. Well, what we can do now is do associativity, so we can flip this around and have Q or P, not Q, therefore P, which is what we're going to do. So on line 5, we're going to flip our things around. We're going to have not T or not N, and that's from line 3 and commutativity. And then we can, with that form, P or Q and not P, we have a disjunctive syllogism from not T or not N and not T. And from that, what we can conclude is not N. So we get not N from 4, 5, and a disjunctive syllogism. Now, I think we can fit this under our first proof. What we have is just 2 premises again. So we're going to have K and H. Let's do K and H. Might have to write a little bit smaller. K and H or K and L. And then our second premise will be not L. And what we want to conclude is H. This is actually, well, these are pretty cool. What we can do, right, is we can, if you look at number 1, it's like backwards distribution. So number 1 is logically equivalent to K or H and L. Or, no. It's equivalent to K and H or L. That's going backwards at distribution. So 1 and distributive dist. So we get K and H or L. Now what we can do is simplify this line and just have H or L. So this comes from 3 and simplification. This is one of our rules of implication. The next thing we can do, right, is associativity. So we get L or H, and this comes from 4 and associativity. And then we have another disjunctive syllogism on our hands. So we can conclude H from lines 2, 5, and disjunctive syllogism. So that wasn't too bad. These proofs were pretty straightforward. So now what we're going to do is talk about the next 5 rules of replacement and get into some less straightforward proofs. But you know what? Things aren't always easy, so we got to learn how to do the difficult stuff. So the first of our 5 that we're going over is transposition. Transposition. And our shorthand for this, we just write trans. I'm going to do a little underline so it's clearer. Now, what does transposition tell us? Transposition says that if we have P then Q, that is logically equivalent to not Q, then not P. Pretty straightforward. The next thing we want to look at, let's go back to our white color, is material implication. So we have material implication, or just implication, because we're going to shorthand this with imp. What is this going to tell us? Material implication tells us that if we have P then Q, that is logically equivalent to not P or Q. Not P or Q. All right, 3 more to look at. We want to look at material equivalence, or you could just say equivalence. And then the shorthand for this will just be equiv. So we have material equivalence, equiv. And the U and the V kind of look the same. Let me erase that. There we go, material equivalence. And what material equivalence tells us, right? This is actually a pretty straightforward one. I think the first 2 aren't really intuitive, but this one is pretty intuitive. Is that if we have P if and only if Q, that is logically equivalent to P then Q and Q then P. And we've talked about that before. It's also logically equivalent to P and Q, so P and Q, or not P and not Q. And that should make sense, right? Because remember, P if and only if Q is only a valid statement if P and Q share the same truth value, right? So either P and Q are both true, or P and Q are both false. Hence, P and Q, or not P and not Q, right? That one should make sense. It makes sense to me. Maybe it'll make sense to you with some practice and some examples. It's always nice to do an example. So the next one we're going to look at, and we got 2 more, is exportation. Exportation. And this one, we just denote EXP. Exportation. There you go. Exportation says that if we have P and Q, then R, that will be logically equivalent to P, then Q, P then Q then R. So P and then Q and R is, Q then R is in parentheses. And then the last one, this is going to be a pretty easy thing to understand, is a tautology. Tautology. And what this just tells us is that P is logically equivalent to P and P, right? So you could get that, you could get that from simplification and addition, but it's also logically equivalent to P or P. This is, and you could go from P to P or P using, that comes from addition. Sorry, P and P comes from conjunction. So you can just add P onto P to get P or P, but you couldn't go backwards. Now you can. If you have P or P, that's a tautology. You can just say we have P from that. So now, we have 8 rules of implication, 10 rules of replacement, and I'll be honest with you, this is where stuff gets difficult, because we have 18 things to work with for our proofs, and you need to be able to remember all of them on the spot and see which ones are useful and which ones are useless on the spot, and it's difficult. The only way to get better is to practice, which is why we're going to do a couple together. Now, this first one we're going to do is pretty difficult. I spent a good amount of time thinking about this. But then the second one we'll do after this will be easier, I think. So bear with me. So this is what we have. Our premises are F then G and F or G. And then our conclusion is G. So my kind of thinking for this, right, is, all right, we have 2 premises that include both an F and a G. And our conclusion only has G. So we want to get rid of F, right? Well, one thing I know from material implication is that we can move back and forth between statements that are disjunctions to statements that are implications, if something, then something. So I know I can do that, And I also know that maybe if I have a hypothetical syllogism, right? What I could do, I can do a hypothetical syllogism where F is in the center and maybe two G's are on opposite ends. And I can remove F from this equation entirely. Now I'm not sure if that's going to work at all, right? That you're not supposed to know if your proof is going to work on your first try. But we're going to go with it. If it doesn't work, we'll just try something else. If it does work, good for us. We're done. So that's the first thing we're going to do is we want to switch our F or G using implication. So that's what I'm going to do. So what does implication tell us? Actually, the first thing I'd like to do is double negate our F. Right? So here's an example of us working within a line. We went from F or G to not F or G. And that's from line 2 and double negation. And now what I want to do is use material implication, because material implication tells us that this right here is equivalent to not F, then G. Not F, then G. There you go. So why is that going to help us? Well, first what we're going to do is write 3 and then implication. And then for line 5, what I would like to do is flip it around. I want to get G on one side and F on the other. And we can do that using transposition. Transposition tells us that what we can do is essentially negate both of these things and flip them around. So I can make this not G, then not F, right? So that comes from for and transposition. For and transposition. Okay. Now I'm seeing that I probably didn't even need to double negate F in the first place, so I could probably remove a line or two from this proof, but it doesn't really matter. Doesn't really matter. We're not going for perfect proofs here. We're just getting a nice introduction to them. But now that I have G and not F, what I'm going to do is double negate that. So yeah, I definitely didn't need to negate it in the first place. I'm going to make it not G, then F, right? And this comes from line 5 and double negation. Okay, cool. So now I have what I want. I wanted to do a hypothetical syllogism where F was in the middle, and I could do that with lines 1 and 6, right? So with hypothetical syllogism, what I conclude is not G, then G. And that came from where? It came from lines 1, 6, and hypothetical syllogism. Okay, so we got rid of F. That's good. Now, what I think I can do is make this a conditional statement disjunction, and then hopefully use tautology to deduce G. So using material implication, I can go from not G then G to not G or G. So that was from 7 and implication. Now what I could do is use double negation to just have G or G. And that came from line 8 and double negation. And this is a tautology. This is just equivalent to G. So this is from 9 and taut. And we made it to the end. Now, like I said, this was not an easy one to think of. I tried 2 different things before I tried this, and this one still wasn't even perfect, as we realized halfway through it. So, don't be discouraged if you can't get a proof right on the first try. You have to make mistakes to learn what not to do, and then to learn what you should try. So, don't be discouraged if this is difficult at first. You'll get the hang of it. The next one we're about to do, though, I think is a lot easier. I mean, at least it stuck out to me. Maybe the first one was easy for you. But personally, the second one that we're about to do, the answer stuck out pretty obviously. So we have these premises. Number 3 is going to be not R, then not Q. And then 4 will be S, then T, then P. S, then T, then P. And the conclusion that we would like to derive is P if and only if R. Now, the reason that this was, I think, really easy for me to see is because when I see a biconditional, when I see if and only if, I immediately think, okay, I want P then R and R then P. Now, that's not always going to be how the proof goes, but it was just my first thought, and it was nice enough that in this situation, it worked out. Sorry, this is not P then G. This is supposed to, that's blue. This is supposed to be P then Q. There you go. Yeah, so my logic was like, okay, maybe I can get P then R and R then P, and it turns out we can get that very, very easily. So, on line 3, what we can do is material implication. Material implication, right? And what that's going to give us is Q then R. So this came from line 3 and implication. And now immediately from lines 1 and 5, I have a hypothetical syllogism. So I have P then R. P then R from 1, 5, hypothetical syllogism. Cool, I got P then R. Now I just need R then P. Well, I have lines 2 and 4 that I still haven't used, and I already see a way that I can get that. If we do something to line 4, what we can have is S and T and then P, and that comes from exportation. So we can derive S and T, then P from line 4 and exportation. And now on line 2, I have R then S and T. So I see another hypothetical syllogism, right? So from lines, what lines are it? From lines 2 and 7, I can conclude R then P using a hypothetical syllogism. Now I have P then R and R then P. Let me use conjunction. So I have, let's see, I have P then R, and I have R then P, right? That comes from, what lines are that? That's 6 and 8. Comes from 6, 8, and conjunction. And now this is equivalence, material equivalence, to a biconditional. So we get P if and only if R from 9 and equiv. So that one, I don't know. For me, that one was easier than the first one. Maybe it wasn't. If it wasn't, that's okay. Some of us are better at, maybe you're better. I'm sure there's a person out there who's better at the first proof than I am. But don't compare yourself. You know, it's all up to comparing yourself to yourself and how you improve. Anyway, with that tangent aside, if you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.